Good evening, everybody. Today we will see, after the brief introduction about the magnetochemistry, how the magnetic properties can help the corresponding course in chemistry when we try to find the magnetic properties of several metal complexes. So, if we have a very simple copper compound which is in the environment of some ligand, and if we try to find out both theoretically as well as experimentally the corresponding mu effective values. So, how we can determine these mu effective values for simple mononuclear paramagnetic compounds, because this area is now has become a very complex one after the introduction of so many cluster or cage like complexes. So, when we see the cage complexes where large number of metal ions are there, such as the most well studied example is a compound containing 12 manganese ions, and not only 12 manganese ions, but the manganese ions are present in two different oxidation states like manganese 3 and manganese 4. As a result, we can have some good idea depending upon the corresponding d electron configurations. That means the dn values, the number of unpaired electrons present in manganese 3 and manganese 4. They, when placed in a typical coordination environment, whether the typical coordination environment which is the most preferred one is the octahedral one. In that particular case, the total number of unpaired electrons present in different manganese centers and how one particular manganese center is interacting with the other manganese center, this gives rise to a typical area where we can consider that magnetic property can be utilized for identifying these cage or cluster like assemblies. Here we see that this particular thing, that we have the molecule, so we can consider them as molecular magnets. So, these molecular magnets are very interesting and very exciting area nowadays to know these molecular magnets, because this gives rise to 2 or 3 different branches when a particular single molecule can function as a magnet with some characteristic and interesting property. We can call it a single molecule magnets. So, this SMM is nothing but single molecule magnet, and also we can have SCMs. So, magnets, SCMs, which are single chain magnets. So, these are rather more complex area where we can store data, where the molecule can have some other interesting behavior and properties, because these are the most emerging area nowadays where we can understand the magnetic properties of big molecules having large ground state spin values. That means large number of unpaired electrons are present within the molecule. But before going to talk all these things, let us have what happens when we have a single unpaired electron in a metal complex like a copper 2 complex of 2 bidentate NN donor ligands. Since we all know that this is a 3D9 system, and whatever coordination environment or coordination geometry we can put around the copper ion, in a 4 coordinated system, like it can be either a tetrahedral geometry or a square planar geometry, we basically get the corresponding magnetic moment what we can measure in the solid state if we can get this compound as a solid powdered one. So, using the solid powdered compound we can determine the corresponding magnetic moment, where we can get the corresponding paramagnetism, whether this paramagnetism is n equal to 2, n equal to 1 or n equal to something else, that we can find out. That means, the number of unpaired electrons we can determine nicely through the measurement of these mu effective values. So, it cannot be n is equal to 2, it will be n is equal to 1. So, for n is equal to 1 system where we can have one single unpaired electron, we can determine the corresponding paramagnetic behavior of the system. So, we get a compound which is paramagnetic in nature, and it is also magnetically dilute system. So, what is that? So, magnetically dilute system means we have individual centers which are well separated. So, it means if we have the second center over here having again one unpaired electron on the second center, we see that these two unpaired electrons will not interact. They are at quite large distance, even if we determine the corresponding solid state structure. And within that solid state structure, if we get the crystal packing and we find the corresponding distance between these two copper centers, we find that they are at very large distance. So, they cannot show any kind of interaction. That means, what we can know that these two unpaired electrons, if they are close enough, they can interact with each other, and sometimes they can share, such as two magnetic orbitals, that magnetic orbital of this copper center can interact with the magnetic orbital of the second copper center, and as a result we can have 2 or 3 different types of rather magnetic interactions. So, when we have a typical paramagnetic center in magnetically dilute system, where individual paramagnetic metal ions are well separated by the ligand system, we get the exact values of the theoretically predicted as well as experimentally predicted magnetic moment values related to the number of unpaired electrons present. But when we have a magnetically concentrated one, so if we have a magnetically concentrated system, then we see that we can have two individual centers. What we know that we can have for simple copper acetate. So, in case of copper acetate, which is basically a dimer, and this basically connected like this. Four acetate groups are attaching like this, and the individual copper centers are in square pyramidal geometry. So, this is the corresponding square pyramidal geometry. And so, we find that individual magnetic orbitals on one copper center is interacting with the second one. So, this is Cu2 OSC whole 4 dot 2 H2. This is the basic structure of simple copper acetate salt, which is basically a dimeric one. So, we get a dimer, and in that dimer these two unpaired spins can definitely interact with each other, and that interaction can also be measured experimentally by determining the corresponding magnetic moment to the system and when they are interacting in such a manner that overall magnetic moment can be increased, we get a ferromagnetic interaction. And if the interaction diminishes the total magnetic moment of the system, we get some anti-ferromagnetic interactions. The interactions can thus be ferromagnetic or anti-ferromagnetic in nature. So, these things, how we can determine all these things, that basically depends on the different energy levels. So, the different energy levels for these systems. So, if we can have several energy levels for a particular structure of this electron distribution, and if they are separated by some energy value, say delta E, and we will find that if we can have two such levels, so we can have two options for these two unpaired electrons on the two copper centers. So, in one case for ferromagnetic interactions, we can have the two unpaired electrons in two different orbitals, and this delta E value is small, so that we can push the second electron to the other level. But when this particular value is large, we basically get the pairing of these two electrons. So, the first one can be considered as a ferromagnetic interaction, and this can be considered as anti-ferromagnetic interaction. So, depending upon the temperature utilized for the measurement, that means if we can go for variable temperature magnetic susceptibility or magnetic moment measurement, we can see that how we can populate the different energy levels, because depending upon the available thermal energy, we can have some comparison of these energy levels for the distribution of different unpaired electron into the system. So, from the very basic Curie equation, what we have seen, the Curie equation gives us the corresponding dependence of the susceptibility term, the molar susceptibility chi m, which is proportional to 1 by T or is equal to C by T, where C is the Curie constant. So, that we have seen in our last class, that this particular term, because this particular term, the molar susceptibility, is very much related to the corresponding mu effective value or the mu spin only value, if we are considering only the spin magnetic moment or spin angular momentum for the corresponding values for the spin only magnetic moment. So, if we get that particular value for this C by T, and this C can be equated to therefore chi m T, and this relationship also gives us the corresponding value for n mu square by 3 k, where k is the corresponding Boltzmann constant. And this basically gives us, this particular relationship also gives us therefore the mu values, which are nothing but root over 3 k T by n beta square in terms of the corresponding values in the Bohr magneton, which will basically, if we try to find out the entire constants, if we put, that gives us the magnitude of 2.84 into chi m T. That much Bohr magneton we can find out. So, it is a very simple technique where we can measure the corresponding molar susceptibility values, and if we multiply with the temperature and its square root of this when multiplied by 2.84 is a constant value, we get the corresponding mu value. So, our problem for determining this magnetic moment is that whether for a particular system like copper compound, any simple copper salt, say copper sulfate pentahydrate, and the one just we have seen, which is copper acetate. So, if we can have these two compounds in our hand, we want to measure the corresponding mu values for them. So, experimentally we can determine the corresponding magnetic moment of these compounds, and also if we get the corresponding coordination compound or coordination complex like this, so it has several other components like diamagnetic parts which are coming from the perchlorate anion or the ethylene diamine backbone also. So, we should have some diamagnetic correction also for this measurement that we will see afterwards. So, for these things, that is, we can calculate out the corresponding mu value for all these compounds, and that basically tells us the corresponding magnetic properties of these salts, the copper based salts or the corresponding copper compounds. Even we can determine these mu values for copper ion, the 2 plus or say 1 plus, because 1 plus would be diamagnetic, which has a 3d 10 electronic configuration which is diamagnetic. So, copper 2 plus or copper 1 plus which is present in biological samples also, that we will discuss afterwards in detail when we will study little bit about the metal complexes in biological system. So, these are such as in hemocyanin. So, in hemocyanin type of molecules we can have the copper center, and that copper center can give some paramagnetic behavior that we can determine very easily. So, whatever this mu value we can determine is that of this any single molecule. So, it is the magnetic moment of a single molecule, and since we have utilized the corresponding n value, the Avogadro number into the expression. So, this susceptibility term what we are using over in this equation is nothing but the corresponding susceptibility of one Avogadro number of molecules. So, this is the corresponding susceptibility term for one Avogadro number of molecules. That is why we consider it as a corresponding molar susceptibility term. Similarly, we can have the corresponding volume susceptibility which is known as chi v, and when we consider it for the per gram susceptibility, we can consider that gram susceptibility values. So, we have the typical constant, that means the corresponding Bohr magneton, the beta value, the beta is equal to nothing but we can have SI unit and non-SI units. In this particular case, beta is equal to 0.927 into 10 to the power minus 20 arc per Gauss, and we can have also the Boltzmann constant value k. K is equal to the corresponding Boltzmann constant, which is 1.3805 to 10 to the power minus 16 arc per degree. So, if we put these values, we will get some interesting informations related to the corresponding magnetic moment, the molar susceptibility, and these distributions, because whenever we get these particular delta E values, we at the same time we should have some basic idea about the corresponding width for the thermal energy, that what is the available thermal energy at a particular temperature. So, if the temperature is in the range of 300 Kelvin, we get about kT value equal to about 210 centimeter inverse. So, this particular width basically can control the population of these different levels by these unpaired electrons. So, we just have all these good informations for these magnetic properties, and we basically utilize the number of unpaired electrons. N is equal to number of unpaired electrons for determining the corresponding mu effective or mu spin only values, because this N is directly related to the total spin values for the system. So, for a simple coordination cage compound or coordination cluster compounds, we see these S values are very high. Similarly, these S values can also will find in case of lanthanides, where we have 7 f orbitals, and 7 f orbitals can accommodate 14 electrons. So, the number of unpaired electrons present in all these lanthanides or the lanthanide bearing corresponding metal complexes are having high S values. So, that is why for making these cluster compounds or the cage complexes, immediate choice for the metal ions would be the corresponding lanthanides if we try to have high ground state spin values, that means the large spin molecules. So, we have N values which can be utilized for determining the mu. So, if we have D4, D5, D6 and D7 electronic configurations in octahedral complexes, then magnetic measurements can predict the weak versus strong field for the corresponding available crystal field. So, this is the direct application of the corresponding crystal field theory. That crystal field theory is giving us two different forms, that means the weak field form and the strong field form. And for D4, D5, D6 and D7, so far we have been able to calculate out the corresponding crystal field stabilization energies for these electronic configurations, because they can have, depending upon the number of electrons in T2G and EG level, we can have the corresponding CFSE values different. That we have seen also when we have applied the CFSE values for ionic radii, for hydration energy, for spinel structure and so many cases. So, now if we have the strong field and weak field case, then the distribution of the total number of electrons from the free ion, that means if it is a cobalt 2, we have a 3d7 electron configuration. Then in octahedral field we can have two different dispositions, that means we have the corresponding configuration for occupancy in the T2G and the EG level, and we have different number of unpaired electrons. So, simply by measuring the magnetic moment, we can determine whether the corresponding complex is a weak field complex or a strong field complex. Similarly, in case of several iron compounds, we have seen that there is a spin state equilibrium, and that spin state equilibrium is also very much temperature dependent. So, as at a particular temperature we see that a system can go from a low spin case to a high spin case as we increase the temperature, then we can identify that there is a spin state equilibrium, and at different temperatures we can have different magnetic moments. So, that also can be determined if we simply measure the magnetic moment of these compounds showing different number of unpaired electrons from one state to the other. But in case of tetrahedral complexes where delta tetrahedron is less than delta octahedron, we only get high spin complexes. So, for a typical distribution of these unpaired electrons in the different levels, we will find only the high spin configuration for delta T, which is very much less than and is 4/9 of the delta octahedron, and accordingly we can have the corresponding number of unpaired electrons, and we determine theoretically as well as experimentally the corresponding magnetic moment of the compound, such as when we have the cobalt which is bound to some ligand like thiocyanate ligand, we get the corresponding tetrathiocyanate or cobalt 2 compound, and we get the corresponding magnetic moment exactly matching with the number of unpaired electrons which should be available for 3d7 electron configuration in tetrahedral environment, which is high spin obviously. So, we just go for this equation for determining the corresponding electrons in the different systems. So, if we can see that how we calculate out these number of electrons, whether we have 1 unpaired electron, 2 unpaired electron to up to 5 unpaired electrons, and if we put these values in this equation, n value equal to 1 or n value equal to 5, we get the corresponding mu values in mu b is nothing but the Bohr magneton, and we can calculate it out. This is the calculated values of the corresponding magnetic moments is 1.73, 2.83 to up to 5.92. And when we determine these values experimentally, we will find that in case of titanium in trivalent state, that means titanium 3 plus, the corresponding magnetic moment is very much equal to that of the theoretically predicted value. That means whatever we are determining as the experimental magnetic moment, which is equal or close to equal to the corresponding theoretically predicted spin only values. So, these spin only values are very much matching with that of the calculated or the experimental values for these magnetic moments. So, we do not have any orbital contribution, because we have seen that when an unpaired electron is present in a system such as in a metal complex, we will see that it has its own spinning motion around its own axis as well as it has an orbital motion. So, both these two motions can generate the corresponding moments. So, we can have spin angular momentum as well as orbital angular momentum values, and as a result we can have the spin moment as well as orbital moment towards the total magnetic moment of the system. Similarly, for 2 unpaired electron and 3 unpaired electron system and 4 unpaired electron system, we can have a magnetic moment which is very much close to that of our spin only values. So, these spin only values can be very much useful when we have a particular arrangement for the first transition series ions, because whatever we are talking that we have the available thermal energy. So, we have the corresponding available thermal energy in terms of the K2 values, and this thermal energy is basically can control the corresponding magnetic properties of the metal complexes. So, these can basically control the magnetic properties, and we can determine the mu effective or mu spin only what we are thinking of, which are the main contributors for the magnetic moments at different temperatures. So, this we can determine at different temperatures, and when we do so, we will see that the corresponding number of unpaired electrons which are available, they are basically coupled in a fashion which we already discussed, the corresponding Russell-Shalders coupling scheme. So, this RS coupling can be operative there, and a particular term we can have. So, a particular term we get, and which has typical S values and L values. So, this is due to the corresponding number of unpaired electrons, and this is due to the corresponding orbital motion or orbital angular momentum values, which can contribute to the corresponding magnetic moment. So, when these things are happening, so for a particular S value and particular L value which is contributing for spin magnetic moment and orbital magnetic moment, so we can have through these two L and S values, we can have the corresponding coupling scheme which we can consider as the corresponding J values. So, the different energy levels what we can have is due to the presence of different J values. So, from the same L and S values, but due to the different types of interactions for these J values can range from L plus S to L minus S. So, if we have a ground state term of 3F, so for 3F we know now what are the values. This is corresponding spin multiplicity which is 2S plus 1. Therefore, here S is equal to 1 for a spin multiplicity value of 3, and then F value also we know that the corresponding L value is equal to SPDF, that means 0, 1, 2. So, this L value equal to 2. So, 2 is equal to L. So, this combination, that means now we get this S value and the L value. So, this combination, that S is equal to 1 and L value equal to 2. So, this L plus S, that means we can have the corresponding values of this SPDF. So, this is 3, S is equal to 0, P is equal to 1, D is equal to 2, F is equal to 3. So, this should be 3. So, 3 and 1. So, we can have the total value from L plus S to L minus S, that means 4, 3, 2. So, these are the corresponding values for these J. So, we have for this 3F ground state term, we are having 3 levels with J values. These are the J values 4, 3 and 2. So, we have a level which is 3F4, then 3F3 and 3F2, and these 3 levels, when they belong to this 3F term and when there is no such splitting, we consider this as a multiplet. So, this is the corresponding multiplet, and each of these states, that means if we have J value equal to 4, J value equal to 3 and J value equal to 2. So, each of these states corresponds to a particular energy. So, they corresponds to a particular energy value. So, now if we see that depending upon the available KT value, if we have the different levels, so we can now think of the corresponding populations of these levels. So, populations of these levels are therefore important. So, population of these levels basically give us some idea that whether our magnetic moment will be due to the entire population of the ground state or the excited state or the second excited state. So, this particular case, the multiplet width is important. So, we just see how this multiplet width can control the corresponding magnetic moment and what particular formula we can use to determine this multiplet width. So, there will be three different such cases where we can have these variation. The first one is where we have the width is large compared to kT. So, when the multiplet width is large, which is large compared to kT. So, if we have a multiplet width which is large compared to kT, we will see that we have the different j levels such as j is equal to 4, j is equal to 3 and j is equal to 2. So, this multiplet width is large, that means this separation is large and the magnitude of this kT is small. So, the thermal energy available, say we are measuring the corresponding magnetic moment from room temperature down to say liquid helium temperature or liquid nitrogen temperature. So, this liquid nitrogen temperature and liquid helium temperature are useful for determining these magnetic moments at low temperatures. So, this liquid helium temperature is around 4.2 Kelvin and this is 77 Kelvin, and down from 300 Kelvin, which is the room temperature magnitude for the corresponding available temperature in Kelvin scale, and your kT value is close to 210 centimeter inverse. So, this multiplet width for different j values, which is j is equal to 4 or j is equal to 3 or j is equal to 2 is large. So, what happens that whatever number of unpaired electrons available over there, they will entirely populate the corresponding ground level or the lowest energy j level. So, in this particular case, what we see that the corresponding state, that lowest energy j is only populated. So, this lowest energy j, if this is the lowest energy, so lowest energy j is only populated and j is now a good quantum number instead of L and S. So, the entire magnetic moment can be controlled by the corresponding mu j value. So, we can find out the corresponding magnetic moment in terms of the mu j value, and now the Curie equation, will take the form in terms of the corresponding mu j, which will be the chi m equal to n mu j square divided by 3 kT, or mu j is equal to g into J into J plus 1 into beta, where G is the gyromagnetic ratio. This ratio has some relationship with the corresponding quantum numbers, and the multiplier for the magnetic moment is 1 plus J into J plus 1 plus S into S plus 1 minus L into L plus 1 divided by twice J into J plus 1. So, for situations like this, when we have this multiplier which is large compared to kT, we can basically use the corresponding equation which belongs to the J value, and we have to have the corresponding term which cannot be utilized for determining the corresponding L and S value. So, we have to use the corresponding J value to determine the corresponding magnetic moment. So, that we will see how the first transition series elements or lanthanides can deviate from these calculations if we can theoretically predict the corresponding values related to these magnetic moments. So, the second case, which is that of opposite to this particular situation, that means where the multiplier with this small, the previous one is large compared to kT. Now, the multiplier width is small compared to kT. So, when it is small, so the coupling between L and S, so in the previous case the coupling between L and S is strong. So, we have the J which is a good quantum number, but now the coupling between L and S, the orbital moment and the spin moment is poor, and as a result these two individual terms maintain their individuality. So, they basically maintain their individuality, and we now get this chi m value compared to this one as n mu L plus S square divided by 3 kT. So, instead of J mu J, we have mu L plus S. So, in this particular situation we can find out the total values related to mu L plus S. So, we can compare the magnetic moment theoretically, whether we are getting a magnetic moment using the mu J equation or mu L plus S equation or mu S equation. That means, theoretical prediction will tell us that whether our magnetic moment, the experimentally determined magnetic moment, can follow a mu J equation or mu L plus S equation or mu S equation only, because the mu S equation is only valid for mu spin only magnetic moment values that is available for the first transition series elements. So, this basically gives us the corresponding equation in the form of Curie equation. So, what we have now, mu L plus S like that of mu J, where we can utilize, instead of using J as the good quantum number, we can use L as the useful quantum number also, multiplied by 4s into s plus 1, what we can have for the spin only equation into beta. So, these are the thing where we can have the multiplier which is small. And the third case is little bit complicated, where we have these two levels, that means the available thermal energy for the typical KT value and the corresponding width, they are comparable. So, when the width, the multiplied width is comparable to KT, we get a situation where we see that the individual things, that mean the individual ions, how they are being populated for the different levels. For that we can have the summation over the different J levels, that means the population of the different J levels with those the Gj values for those levels in Gj square into J plus 1 divided by 3 KT into beta square. This is the form of the corresponding new Curie equation for a situation where the multiplied width is comparable to KT. So, these Nj values are proportional to the corresponding multiplicity related to the J value and exponential minus delta E by KT, and that is the corresponding energy what we are talking about for these different levels. So, if we have J is equal to 2, J is equal to 3 and J is equal to 4 values, and the energy gap between these two levels, if these are delta E, then this delta E term can come over here, which is nothing but the energy difference between the ground level, where we are considering the energy as 0, and a particular J level. That means J value equal to 3 or J value equal to 4, that means the first excited level. This is the first excited level and this is the second excited level. So, if we get this and if we bring the proportionality constant C, so it will be C into twice J plus 1 into exponential minus delta E by KT, and as a result this chi-m equation will take the form which is involving the corresponding delta E term also, which is equal to n by 3 KT and sum over Gj square beta square J into J plus 1 into this term twice J plus 1 e to the power minus delta E by KT divided by these levels, that means twice J plus 1 e to the power minus delta E by KT. So, what we get now that the molar susceptibility now can have all these terms, that means it can have the values of this J, the Gj values and the corresponding energy term. So, therefore, it is a complicated function of J and T. That means the most difficult and most complex situation will arise when our multiplied width is only comparable to KT. That means we cannot ignore the corresponding terms related to the relative distribution of all these levels. In one case it is only the ground state is populated, in other case these higher levels are also populated, and we are considering both the L and S values, but when the width is comparable only, then only we have to bring the corresponding energy gap between these levels and how these levels are populated. So, this basically gives us some idea that if we can determine the corresponding susceptibility term with respect to temperature, then only we can have some good idea about the relative population of these levels. So, as a result, if we just apply the different terms for these different values, what we have seen that for titanium, vanadium, chromium, manganese to up to copper 2 plus, and what we can calculate it out in terms of the corresponding values with respect to the S value. Now, if we just simply take the example as the corresponding S, not only the S value, but also the L value. So, if we just consider the corresponding L values at the same time, so if we have the titanium 3 plus, which is 3D1 case, and that 3D1 case basically gives us some information that we can have the corresponding S value and the corresponding L value. So, we have it is half and L value equal to 2 for the d electron, and the spectroscopic symbol for this would be 2d 3 by 2. So, for this basically we can utilize the corresponding mu j equation, corresponding mu s equation, and mu L plus S equation. Theoretically, we can utilize these to get the corresponding different values and finally the observed values of the magnetic moment. So, in the previous table what we are seeing there, we are basically looking at the corresponding spin only values, which is 1.73, and the observed values are also ranging from 1.6 to 1.8. So, this is the thing that where we can have the corresponding value, which is n is the number of unpaired electron, S is equal to half, and mu value is equal to 1.73. So, this is nicely looking nice for these corresponding values, but if we calculate it out the corresponding mu j also, it would be less, it is 1.55 and it would be 3.00 for mu L plus S. So, basically what we are fixing over here, that we have a small value for these magnetic moments when we consider the mu j equation, that means j is a good quantum number. If we consider that there is no orbital contribution, then mu s is the good equation to determine the corresponding magnetic moment equal to 1.73, and in fact experimentally determined values are close to these values. But if we consider that orbital contribution is there, the L values are also contributing towards the magnetic moment, then the upper limit of this magnetic moment is equal to 3. That means, if orbital contribution is there, our total magnetic moment can go beyond the spin only value and it can reach up to a magnitude of 3.00. Similarly, in case of vanadium 3 plus, which is 3d2 electron configuration, S value is equal to 1, L value equal to 3, the term is twice F2, and as we have seen in our previous table that mu spin only value is equal to 2.83, and the experimental values are also ranging from 2.6 to 2.8. But when we bring the other two values theoretically calculated as using J as the quantum number and L and S both as the two quantum numbers contributing towards the magnetic moment, it will be 1.63, which is in the lower range, but in the higher range it is 4.47. Similarly, for chromium 3 plus, we can have 3D3 situation where S value equal to 3 by 2 and S value equal to 3, and we have 4F3 by 2, and spin only values we have seen it is 3.87 and experimental values are 3.7 to 3.8, which is matching with the spin only values. But if we think of the corresponding mu j equation, it is very less, it is 0.77 only, and the upper limit for L plus S is 5.20. So, when we continue, when we fill up the entire table, in our next class we will find that there will be some values where the mu spin only is not the exact values, but it can have a value close to mu L plus S. That means, it can have the corresponding orbital contribution towards the magnetic moment. Thank you very much.